Hey everybody, welcome back to physics. Today we're going to be talking about polarization of light and reflection of light. It has nothing to do with kazoos. So I want to talk about some more things that light does, some interesting things about light that we could observe in nature. We're going to focus on polarization or reflection today. In the future we'll be talking about things like refraction. All right, so let's just dive in and get started. Where's my clicker? All right. So here's the thing about polarizers. You might have heard this term polarization in your everyday life, things like polarized sunglasses or polarized filters on things like cameras. But what is polarization and how does it work with light? What does it actually do? Well, we learned that light is a transverse wave, and transverse waves oscillate perpendicular to the direction of wave travel. So if the wave is heading this way, transverse waves will oscillate perpendicular to the direction of wave travel. Now, we said we were looking at waves that oscillate up and down as they travel this way, but it could also oscillate this way. This would also be a transverse wave as it heads forward. It could oscillate in all kinds of different directions in this plane. As long as the wave is oscillating in this propagating in this direction, it could oscillate in any other direction within this plane, if that makes sense. Now, we know that light is a transverse wave because of this idea of polarization. So take a look at this diagram and then we'll define polarization. Here we have non-polarized light. That's the light that's closest to us here. This light can could be oscillating up and down, diagonally, left and right, but the wave is propagating forward. This is unpolarized, non-polarized, because it's oscillating in all kinds of directions that's heading towards the polarizing filter. And then it reaches this blue picket fence looking thing. And then the non-polarized light reaches that filter. Notice that the filter has spacings that are vertical, up and down. So when the non-polarized wave reaches the polarizer, only the wave that's oscillating up and down can pass through the polarizer. And now this non-polarized wave, which could be light, passes through the polarizer and it becomes polarized, which means it's forced to oscillate in a single direction. Here it's oscillating up and down. Now notice when this light reaches the next polarizing filter, those spacings are horizontal. So this vertically polarized light cannot pass through that second filter. So what does this have to do with our everyday life, polarization? Well, this proves that light is a transverse wave because a longitudinal wave would be able to pass through both filters no problem because longitudinal waves oscillate parallel to the direction of wave propagation. Now, what's really cool about light is it can become polarized in a lot of different circumstances. For example, when light strikes a puddle, it becomes polarized in a certain direction. And now that polarized light bounces off the puddle and heads towards our eyes. If we have polarized sunglasses and they're polarized in just the right direction, we could actually cancel out the glare from bouncing off puddles or bouncing off other cars. That's the use of polarized sunglasses. Things like polarized filters on cameras can filter out certain types of light. For example, I was actually just watching a video where the cameraman had a polarizing filter on his lens and he rotated the filter. And when the filter was oriented in one direction, you couldn't see through the water that he was pointing the camera at. But when he rotated the lens, the filter, when he rotated the filter, then suddenly you were able to see right through the water because we were canceling out the glare on top of the water. That's the use for polarizers. Not only does it prove that light is a transverse wave, but we could use it to help us observe light better in nature. There's a lot of really cool demonstrations you can do with polarizers. Polarizing filters are pretty cheap if you wanted to order them and play around with them. But you could cancel out light and even make light look some interesting colors if they're oriented just the right way. So what you need to know, the big idea for polarization is that light is a transverse wave and polarizing filters force the light to be polarized or oscillate in a particular direction. And that's really all we need to know about polarization for our level here. Okay. So the next thing I want to move into discussing is the reflection of light. And now this is a deeper discussion than you might think. Before we talk about the reflection of light, we want to talk about two different types of objects in our universe. In our universe, we have luminous objects and we have illuminated objects. Now, what's the difference between those two types of objects? This picture kind of summarizes it pretty well. Luminance, we have this word pointing to the light. This light bulb is an object that is luminous because it creates its own light. Where the floor here is illuminated, that's illuminance. The floor is not creating its own light, but it can reflect light so then we can see it. Okay, hope I'm not moving too quickly. So here are some examples of luminous objects. Again, luminous objects create their own light in the universe. The sun is a luminous object. It creates its own light. Light bulbs are luminous objects. Campfires are luminous objects. Anything that produces its own light would be luminous. And I also threw this little picture here in the bottom right-hand corner. In certain places in the world, there are actually microorganisms in the water. And when those microorganisms are jostled, they glow. And that's what we call bioluminescence. So these microorganisms are creating their own light. That makes them luminous objects. And the cool thing about these areas is you can actually go surfing at night, and the waves and the surf cause these microorganisms to glow, which creates a pretty surreal experience. So these are some examples of luminous objects. Illuminated objects are objects that do not produce their own light. They reflect light from their surroundings. The moon is an example of an illuminated object. It does not produce its own light. When you see the moon in the night sky, it's reflecting the light off of the sun. Trees are illuminated objects. People are illuminated objects. And this little toy car here would be an illuminated object. Think of it this way. When you're in like a dark basement, you haven't turned on the light yet, and you're looking at your hand, you can't see your hand because there's no light reflecting off the hand to head towards your eyes. But when you turn on your luminous objects, your light bulbs, the light can now bounce off your hand, head into your eyes, and we could register that we have something in front of us. Now here's the cool thing about illuminated objects. I said that they need light in order to reflect it back to our eyes. But take a look at this picture here in the middle. See all this green that you see in the trees? What's actually happening is the light is coming in from the sun, reflects, heads to our eyes. But the sun produces all different colors of light. It creates white light, which is a mixture of all the colors. So that white light comes in, strikes the leaves, and the leaves absorb all the different colors of light except for green. Green is the only light it reflects, and that green heads to our eyes. So let's take a look at this red car here. Based on what I said, that means that this car is absorbing all the different wavelengths of light except for red. Red will be reflected off the car and head to our eyes, which raises an interesting question. Is this car red, or is this car every color but red? This car is absorbing all the colors except for red, which reflects out to our eyes, which we register as a red toy car. Okay, luminous objects create their own light. Illuminated objects reflect light. Now, objects like mirrors would also be considered illuminated objects because they reflect light in order for us to see. But what's the difference between this toy car and a mirror? This toy car, we can't see ourselves in the car, but we can see ourselves in mirrors. So what's going on there? Well, when it comes to reflection of light, recall that the law of reflection still holds here. The incoming angle, the incident angle of light, or any other wave, is going to be equal to the reflected angle. And the way we can draw this out is if we have a reflective surface. Here's the normal line. If we have any ray heading in, could be light or it could be any other wave that can be reflected, this incident angle is equal to the reflected angle, measured relative to the normal line. And that holds for any object that can reflect light. Let me erase. Now, depending on the smoothness of the object, we actually get two different types of light reflection. The first type of light reflection is what we call specular reflection. And the second type of reflection is what we call diffuse reflection. When you have a smooth enough surface, like a mirror or like a still body of water, you can get specular reflection. And specular reflection will produce an image when it's reflected off of the surface. Let me draw a little diagram to help you see this better. Let's say we have the light coming in from like a person. There you go. Head's over here, feet are over there. Now, the light that's reflected off this person's head will come in, bounce off the surface, and head over here. So if you follow the light ray, you can see that we're still following the law of reflection. This ray comes in, heads over here, so the light from the person's head will be over there. The light from the person's body heads in, bounces off this smooth surface, and heads parallel to that direction of the headlight, right? And then the light from the legs heads in, bounces off, and here is the light from the legs. Each ray of light remain parallel as they reflect, and an image is formed with the reflected rays of light. That happens off nice smooth surfaces. The light doesn't scatter around. That's specular reflection. That's what we see in mirrors. But diffuse reflection, when we just look at something and see colors, that's because the surface is not smooth. Notice, look at the surface here. It's very lumpy. So if we have our person, if we break down this diagram, here are incident rays. That's the rays that are heading into the surface. And then the reflected rays, we have one ray coming back up here. We have one ray bouncing this way. We have another ray bouncing this way. So if you have the image of a person here, the image can't be formed because the head's over here, the body's over here, and the legs are over here. And now keep in mind that it doesn't just take 3 rays of light to create an image. There's an effectively infinite amount of rays of light that are bouncing off here and reflecting off the surface. They're just showing you 3 rays here, but all of those rays are bouncing in different directions, so it's impossible to hold an image. But the light is still reflected, and that's why we can see things that aren't producing their own light. The light will still reflect off these diffuse surfaces and register in our eyes. Another thing I want to make sure that we're aware of. I said here that the law of reflection still holds for all these bounces. But we're going in all kinds of crazy directions here. Does the law of reflection still hold? Well, we're coming in, we're hitting this surface here. So if this was like the normal line, the law of reflection still holds compared to this surface. But now the surface is kind of pointing in a different direction. Law of reflection holds. And the law of reflection holds here as well. So the law of reflection is still in effect. It's just that the surface is not smooth, so it sends the light rays in all kinds of crazy directions. So to summarize, specular reflection, we can get images from the reflected rays. Diffuse reflections, we won't see any images, but we can see colors from those colors and shapes. Okay. So now I think it's time for us to talk about mirrors. Now mirrors are really good at giving us specular reflection. We've learned how to make these devices and we make them pretty consistently to always give us a nice image when light reflects off of these devices, which we call mirrors. Now, mirrors are pretty cool. I don't know about you guys, but when I was little and you would like look inside the mirror, you would see yourself and you would see you're moving, but it looks like you're looking through a window into a different reality. We know that's not the case because we know physics. But what's interesting about how we model these things is the image from this bottle is actually here. It's a virtual image, which means it's not a real image. There's actually no light rays passing through this point. But our eyes are tricked because in our brains, we think that light always moves in straight lines. So we actually get an optical illusion. When we're seeing this bottle, we are seeing the bottle that's here, but it looks to us that we are looking through a window to see this virtual object through the mirror. And notice how all of these light rays work for mirrors and specular reflection. They're showing you a few light rays coming from the bottom. They bounce off the mirror and they head to our eyes. They're showing us a few light rays from the top. They bounce off the mirror and head to our eyes. Right? We're getting this law of reflection. We're seeing that the image is still going to be in place, but our eyes are getting tricked, and what we're doing is we're tracking this object like we're looking through a window, like that object is right over there. That's what that dotted line represents. So what flat mirrors do, these are the mirrors that you'll normally find in your home. They create virtual, upright, non-magnified images behind the surface of the mirror. Let's break down this statement because we have to know what each one of these words mean. Flat mirrors create virtual. Virtual are not real images. An example of a real image would be like looking through a lens, right? Like a lens for eyeglasses. The images that are created are real images because the light rays actually come off that object, bend through the lens, and hit our eyes. So if we're actually sensing the real light rays coming off the object, that's what we consider a real image. But because there's no true light rays here on this image, that makes it a virtual image. The image is also upright, which means that it's not flipped in the up-down direction, in the vertical direction. Some types of mirrors and some types of lenses, like curved mirrors or certain types of lenses, can actually flip the image on us. And then that would make that an inverted image. But flat mirrors create upright images, and flat mirrors also don't magnify the image at all. Again, if we curve the mirror or if we have certain types of lenses, then we can get a magnified or a smaller image. But for flat mirrors, we see the image as the same size as the object. And the image itself is behind the surface of the mirror. Now you might be saying, Mr. Hatzfeld, we know there's nothing here, so what are you talking about, the fact that the image is behind the mirror? Well, that's the trick that our eyes are being played on us. This image looks like it's behind the mirror, so we say that the image is created behind the mirror. Here are some other facts about regular mirrors. So if you're standing in front of the mirror, you walk closer, the image walks closer to you as well. And when you walk away from the mirror, the image walks away from you too. We know what's really happening is the light from me is bouncing off the mirror going to our eyes, but because the image is created, we can actually track what that image is doing. And when we move away, the image moves away. When we move close, the image moves close. Now the distance between the object and the mirror and the distance between the image and the mirror are always going to be equal. If I move this water bottle closer, or whatever this bottle is, then the image is going to move closer at an equal amount. If I move it further away, the image moves further away at an equal amount. So if this water bottle is, let's say, 10 meters away from the mirror, the image is going to look 10 meters into the mirror. Okay. Another thing about mirrors, I'm sure you might have noticed this, but mirror images are inverted left to right, but not up and down. That's why I said it's an upright image, because it's not inverted up and down. But why is that the case? When we look into a mirror, and we're wearing text on our shirt, right? I look into the mirror and that text looks backwards. What's going on with that? Well, we know that the light coming off of us, that's reflected off of us, bounces into the mirror right into our eyes. But you have to keep in mind that we have some perspective that we need to track. All right. So I made this thing. This is a Ziploc bag that I wrote physics on, right? Now, if I was wearing the shirt, right, I would want to wear it like this. So it says physics, and you see physics. But if I looked into the mirror, I wouldn't see physics. It would look backwards to me, right? Now, the thing is, the light that I'm actually sending out is not this, but it's me looking through it, right? If I took the image and put her up to our eyes, to my eyes. So you see physics, but I don't see physics anymore. It looks backwards to me. Let me show you another thing. So this is you wearing the physics shirt now, right? It looks to me that the physics is pointing in the right direction. It says physics, but as you can see through the camera, it's backwards. So what the mirror is doing, it's quite literally bouncing the light back. What you would see if I just took the image and I put it right in front of my face. It looks backwards, and the mirror is showing you the fact that it's looking backwards from that perspective. From the other perspective, it would look straight. Hope that little demonstration made sense. Okay, so what do you say we try a few puzzles before I let you go for today? Oh, one more quick thing. Different shaped mirrors can cause images to shrink or become magnified. So I don't know if you've ever been to a fun house before, but if we have curved mirrors, like this would be called a concave mirror, if it's kind of like in this direction, or a convex mirror, where it's in this direction. For a concave mirror, now the light is bouncing in interesting ways to make things look different. So whether we have a concave or a convex mirror, these bendy funhouse mirrors, we could magnify or we can shrink images. And depending on where you stand, sometimes we can even flip the image upside down. It's a lot of fun we could have with specular reflection. Okay, so let's try some puzzles. Question number 5. A barrier is between a light source and a mirror, as shown in the diagram below. Use ray diagrams to determine which observers, if any, would be able to view an image of the light source in the mirror. Circle observers that can see the image of the light source. Cross out observers who cannot. Include a short explanation for each one of your answers. 8 points. I don't know what those 8 points count for. You can make them Hatzfeld points. So we want to figure out which one of these observers, where's my marker? Observer A, Observer B, or Observer C can see this light source in the mirror. That means that we need the light to reflect off of the mirror and head into the observer's eyes, right? Here's our observer. I don't know, some hair. Another observer down here. We need the light to head into the eyes because our eyes gather that light, and that's what we understand to be images. And here's the light source. So if we're seeing it in the mirror, we need it to bounce off the mirror and head to our observers. Let's take a look at observer C. Is observer C going to see the object? Well, we have light that's heading in all directions, but the thing is, this light won't be able to bounce off the mirror and head into observer C's eyes. The mirror is blocking the source of the light. Observer C won't see it. This would be an example of saying, stand behind the mirror and let me know what kind of reflection you see. You won't see any reflection behind a mirror, so observer C is out. Okay. Now what about observer B, heading backwards? Well, we need the light to bounce off the mirror from the source into observer B's eyes. Well, this barrier doesn't let light go through. And the only way that we can get it to observer B's eyes, following the law of reflection, is if the light came this way and this way, right? Here's that normal line. Well, this can't happen because the barrier's in the way. So this cuts off the light and doesn't allow the light to head into observer these eyes. Sorry, guy, you're out. But what about observer A? Can observer A see the light source as a reflected image from the mirror? Let's see. Well, if the light source is producing the light, and we need it to go to observer A's eyes, it can bounce off the mirror. There it is. Observer A can see the image. Because the light source will come, it'll bounce off the mirror and it'll head into our eyes. So observer A is the correct answer here. As a bonus extension question, where does it look like the object is according to observer A? When you see things in the mirror, like if A looked, he sees the light source here, but he's also going to see something in the mirror. Where is the image going to seem like it's located in the mirror world? Well, our eyes assume that light is going in a straight line. And we also said that the distance between the object and the mirror and the image in the mirror are going to be equidistant. So this is what we call DI. This would be DO. Those would be equal. So it would look like the image is right here. I think that's straight enough. Maybe it's more like there. Okay. All right. Now again, there's actually nothing there producing light, but it looks like an image is created, a virtual image is created here within the mirror world. And that's what's pretty cool about physics, is we can predict where these objects are inside of our mirrors. Even though we can't get in there and actually measure where this object is, we can still predict where the image is going to be inside of the mirror. This virtual image that's truly a reflection from this object here. Okay, let's try one more puzzle. Here we go. So here's the deal. We have a man, and the man is about 2 meters tall. That's a bit less than 6 feet tall, and standing 1.5 meters away from the mirror. Where is his image located, and how large is the image? And we can report these answers in meters. Okay, so where is the image located relative to the mirror, and how large is the image? Well, we just talked about the fact that the distance between the object and the mirror is always going to be the same as the distance between the mirror and the image. So, because we are 1.5 meters away from the mirror, we can say that the image is 1.5 meters into the mirror. If that man walked to be 3 meters away, that means the image is going to be 3 meters away from the mirror inside the mirror universe. It's not a real thing. Okay, so that's where the image is located, but also how large is the mirror? Well, if we have a regular flat planar mirror, we know that there's no magnification occurring. So if the man is 2 meters tall in real life, there's no magnification. The man, the image within the mirror is going to be 2 meters tall. Now, if we had a funhouse mirror, this might be a little bit different. But because we have a regular flat mirror, image is 1.5 meters away, and there's no magnification, the person is 2 meters tall. The image is 2 meters tall. And now this next question is tricky. It's going to take all of your reflection knowledge in order to figure it out. Try it, and we'll talk about the answer. Regardless of where he stands, What's the smallest mirror necessary for him to see his entire body? This is an important question to ask. It's not just a good physics puzzle, but this will determine how big we make our mirrors in order to make sure that when you're standing and looking at them, we could still see our whole body using the least amount of material possible. Well, we know that he could see his whole body if we were looking at, if we had a full body mirror, right? And how does this reflection work? Maybe that'll help us figure out this question. I know I have a drawing over there, but I'm going to redraw over here. Here's our mirror. And here's our person with eyes. There's our eyes. Boom. Now, in order to see something in the reflection, that means that the light has to come off our body, reflected from another source, obviously, and head into our eyes. And if we want to see our entire body, that means we need to see our feet, we need to see our head, and we need to see everything in between. And I said there's an infinite amount of light rays that are reflected off the body and heading into the eyes, effectively infinite. I don't have time to go through infinite light rays, but if I look at the extremes, if I want to see the whole body, that means if I see the feet and I see the top of the head, I should be able to see everything in between. So, based on what we know about reflection, the light coming off the feet is going to come up, bounce, and head into the eyes, right? Based on the law of reflection. These two angles have to be equivalent. Okay. So, as long as I could see this portion, I could see the feet. If I want to see the top of the head, that means the light has to come in, bounce, and head to the eyes. Again, following the law of reflection. So as long as we can see this point, and we can see this point, everything in between should hold all of the information, all of the reflected light, so we could see the entire image. So the correct answer here, we can see we're cutting his body in half. This is pretty much the top of his head. This is going to be half of his height. So the correct answer is 1 meter. It's a little more complicated than that because we can actually use less mirror than 1 in order to see the whole body, because it's really the distance between these 2 points, which is a little smaller than the top of his head. But it's effectively, this tiny little distance is pretty small compared to the size of half of his height. So as long as we have a mirror that is 1 meter tall and positioned so it's covering the top half of his body, he should still be able to see his entire reflection. If you're feeling ambitious with your geometry, you could try to figure out what this little bit is and how much it takes away from this 1 meter length. But as long as we have a 1 meter length, waist height up to the top, we should still be able to see the whole body. All right, everybody. I hope you enjoyed this little lesson today. Next time, we're going to be getting into refraction, which is a little bit more mathematically intense than what we've been doing so far. But that's okay. We'll be able to do it. Hope everyone's doing well, and I'll see you in the next video.